And so, like I kind of foreshadowed earlier, is that decimals, which comes from the Latin decim, meaning 10, and yes, that's December. We used to have, and so here, this is like an aside, but if December was 10, and November is 9, and October is 8, and September is 6, we get broken when we go to August, July, and then if we start, and then January, February, March, April, those ones don't work quite as well, do they? At least towards the end of the calendar, we get those, and so we used to only have 10 months, but then we added 2 more in the mix, and that just messed everything up. But we care about these decimals, which are really special fractions, because of their connection to our base 10 system. Fractions can have any number as their part. A half, a third, a fourth, a fifth, a sixth, a seventh, it doesn't matter. Any part you can be your unit fraction when we're talking about a general fraction. However, when we're talking about decimals, our unit must always be, their part must always be a power of 10. And so when we talked about place value for just numbers before, we talked about the ones, tens, hundreds, thousands, 10,000s, 100,000s. So that was our powers of 10 increasing. But we can also show them decreasing. So instead of having a whole one, let's look at a tenth of a whole. Or let's look at 100th, or a tenth of that tenth. Or 1,000th, which is a tenth of that 100. And so we have lots of things that, or we have these fractional parts that are now specified to be a tenth of the preceding value. So, writing some number, some decimal in expanded form. So, we're going to do this complete by place value. So, how many tens? We have 1 10, plus we have 2 ones, plus 6 tenths, plus 1 100th, plus 8 1,000th, plus 7, got a little carried away, 7 10,000ths. Because as we march along, each part is a tenth of the size it was previously. And so here I have it marching through 6 tenths, 100th, 8 thousandths, 7 10,000ths. And so in words, it's 12 and 6 tenths, 100th, 8 thousandths, and 7 10,000ths. Or if you wanted to, you could say you have, and this is a fun little fact, you could say you have 6,187 10,000ths. So there are lots of ways in words we could use these. But when I'm talking about expanded form, I'm generally referring to this number at the top. So let me get my pen out. So we have something like that there. That's what I'm talking about when I mean expanded form. You don't need to put it in words. Unless I ask you, I'll say in words. Or I'll give you a word name and I'll say, give this to me in expanded form or decimal form or something like that. And so thinking about fractions on a number line, so the whole numbers are represented in that top one, 0 to 1 to 2 to 3, all the way up to 8. And then each of those units will be partitioned into tenths. So each unit is 10 tenths. And then from there, each tenth, so from 2.5 to 2.6, is partitioned into 10 hundredths. And so this one here, from 2.7 to 2.8, has 100 hash marks between them. And then each of those hundredths is partitioned into 10 thousandths. And so we just keep doing this process further and further and further. And so if we needed to place a fraction on a number, a decimal on a number line, we would essentially follow this practice. We find the whole, and then we zoom in, find the tenth, zoom in, find the hundredth, zoom in, find the thousandth, and then hopefully by then we're done. That we want to stop. Right, so eventually we're going to run out of decimal digits, and so thinking about how we do that. And so we can use the number model or the number line model, but we can also use base 10 blocks. So suppose that a long in the base 10 block, so that's this one. This one is now going to represent 1, not 10, but 1. Well, that means each of these unit cubes now is going to be a tenth. And so if we wanted to represent 5.4, we would have 1, 2, 3, 4, 5 longs, and 1, 2, 3, 4 tenths. And so you can see how they're already starting to make this connection of, well, you could look at it 5.4, or we could look at it as 54 cubes, or 54 tenths. So we have options in how we choose to represent. Now, if we want to model past tenths, so say hundredths and thousands, if we make our cube, which is our 10,000, or our 1,000, this is our 1,000. It's 1,000 cubes. If we make that our unit, our flats become tens. Our flats become tenths. Our rods become hundredths. And our units become thousands. So just like we modeled addition, subtraction, multiplication, division with these for whole numbers, if we just change what they represent, we can extend them and model base 10 blocks, which means if we were able to use expanded or partial products with these to find the products of two whole numbers, we could do partial products with fractions. And so if we say have 2.23 times 1.7, we can just multiply each of those corresponding parts and add up our sum. And so there are types of decimals, right? Not all decimals are created equal. So there are some decimals that you can write with some finite list of decimal points. So like a half is 0.5. There's nothing after that. Or you might have 0.625 or some finite number where it stops. An example of one that doesn't is pi. Right? The number pi is 3.14159, and it just keeps going, and it never stops, ever. Or even an easier one. 1.3 repeated, 1.3333, and it just keeps going. It never stops. Those are called, the ones above this line I just added, are the terminating. And now on the below the line I have two types. One doesn't terminate, but it does repeat. So it's non-terminating but repeating. And then our last one doesn't do either. Neither terminates or repeats. And so we have three types of decimals. And only, this is important, only decimals which terminate or repeat are in the rationals. These ones that neither, you can't see that arrow, these ones like pi that don't terminate or repeat are not in the rationals. They're in what are called the irrationals, which is this double I. Two vertical bars in a line. And so we need it to either terminate or repeat. And we'll talk about terminating first, and then we'll talk about repeating, and that is where we'll kind of wrap up today's big ideas. So decimals that can be written with only a finite number of decimal places to the right are called terminating. And a rational number, so a divided by b, in its simplest form can be written as a terminating decimal if and only if, so this says these two things are equivalent. Terminating decimal is equivalent to the prime factorization of the denominator b contains no primes other than 2 or 5. Let me unpack that. Because we have a half. 2 is either 2 or 5. And so it will terminate. And actually, here's some more examples. 7/16. Because 16 is only powers of 2, it will terminate. 19/40. Because 40 only has 2's and 5's in it, will terminate or repeat. But some that won't. 11/18. 5/26. 9/84. Because some of them have 3's or 13's or 7's. But for it to terminate, it must, or its denominator must be only powers of 2 or 5. And why is that? Well, let me bring up my writing. So if we think back to place value, 1/10 plus 1 100 plus 1 1,000 plus 1 10,000. Right? So we have something that looks like that. If I factor each of these, I have 2 times 5. 2 squared, 5 squared, because it's 10 times 10, or 10 times 10 times 10. 2 cubed, 5 cubed. 2, 4, 5, 4. We can only write a decimal in a terminating form if somehow we can rewrite the fractional parts of it as one of these denominators. That's exactly where this 2/5 and 5, the 2's and 5's comes from. Because if I have, say, a third, there's nothing I can multiply this by to get me a 10, 100, 1,000, or so on in the denominator. But if I have a fourth, which is 1/2 squared, I just need to multiply the top and the bottom by 5 squared. We get 25/100, or 0.25. Right? And so that's why we need to have the fact that's above me. Terminating decimals have only powers of 2's and 5 in their denominator. Non-terminating decimals, like a third, won't, because there's no way we can multiply a 3 and magically turn it into a combination of 2's and 5's. It'll never work out that way. So how do we convert a non-decimal fraction to a decimal? And so I showed you a quarter here, but I'll do another example here with 7/8. Well, first we can check to make sure, will it terminate? And the answer in this case is yes, because 8 is 2 cubed. So what we have, I'll go back to just slides. We have that 7/8 is 7/2 cubed. And like we talked about before, we can multiply by 1 and not change it. And 7/2 cubed. Let's get 3 of those 5's in there. So 2 cubed and 5 cubed, we said earlier, was not our 10th, our 100th, but our 1,000th. And 7 times 5 cubed is too big for me to do in my head. I think it's like 825-ish. 7 times 7 times 5 times 5 times 5. 875. I was close. It was 875. And so that's thousandths, so we have 0.875 thousandths. Tenths, hundredths, thousandths, 875 thousandths. And I should have nice neat work. Now I showed every single step and I didn't use exponents, but I was too lazy to handwrite all of those multiplications by hand. But to just kind of emphasize the key steps, so seeing that we can write it as a power of 2, figuring out what we need to do to get it into our denominator we can work with. If we have commutativity and associativity, we can rewrite these 2's and 5's as 3 10's. There's a typo there, times 10. 7 times 125 is our 875 thousandths. We can also convert decimals using long division. So if we are doing 7 divided, nope, it's important that we write it the correct order. 7 divided by 8. So we have 7 being divided by 8. Well, 8 doesn't go into 7 at all, but 8 does go into 70. So we have 8 times 8 is 64. Subtract, we're left with 6. Add another 0 and bring it down. 60, we can't do 8, but we can do 7. 7 8s are 56. Left with 4. Bring me another 0. 8 times 5 is 40. Subtract. Left with none. And 7 divided by 8 is 0.875. And so you can use whichever form you need to. Now, if it's non-terminating, you wouldn't want to use this approach, right? If it doesn't terminate, there's no process we can use in this to get it as a power of 10 in the denominator. I'm trying to figure out which way I need to point. I point that way, right? And so if it's not terminating, we won't use this process, but we can use this process generally. Whether it terminates or not, we can use this process.